yeah, we're going to chat a little bit about, I think, the use of LLMs today and how to, in particular, customize them for whatever tasks or requirements that you have of these that you have in your own workflows or in your own businesses and so on. So yeah, we can go through a lot of different things, but maybe we can discuss like a little bit of the history of how we got here. I mean, right now, obviously, there's this release of Llama and Llama 2, that just came out a few days ago. That seems to have really opened up a lot of opportunities for academics, researchers, but also the open source community to really start experimenting with customizing LLMs in loads of different ways. And so now there's a whole host of different ways that you can customize your LLM, and there's a whole zoo of models that exist out there. So we're going to talk about all these different approaches a little bit. There's touch on as many as we can. But maybe, Siddartha, I don't know, maybe we can talk a little bit about why would it be useful to customize LLMs in the first place? Like, why not just use a single LLM?
Yeah, we should definitely go there. I think you one point that you kind of like went over just now, and I think is fun to think about in this context, is the nature of some of these things being released, like Llama and Llama 2, right? And when I draw parallels to like other industries, I think it's fairly unique because I think many people now appreciate these things are not cheap to train. There's like serious money that is being put into training on these models. It takes both a lot of like just compute capital, but tons of like human capital. We know how hard these training runs are to keep alive and stable and proceeding in a sensible fashion. So the fact that they're released is to me like imagine like some big industrial company came up with a factory and produced a factory and wanted to share it with the world. Like there's no way to do that in the physical world. Like you have one of these factories, there's only so much of it that you can use. If anybody else wants it to use to build some different kind of widget, I can't give it to you. I just have one copy. Sorry, right? It's not that I'm not being generous. But like these things are kind of a little bit magical that way, right? Like you go off and do a lot of hard work, you produce these weights, basically a few billion numbers, and I share these few billion numbers, and suddenly people can use it as their own factories to like build new things, to do new apply to new tools. So I think that's one fairly unique thing that is worth recognizing. It's very different even from like ML before this, where yes, you could release an algorithm, which in some ways is a recipe, numbers, string of text, whatever, but it's a recipe, but it still involved like a substantial amount of compute you would have to do on your own before you could extract any value, because you have to apply it to your data, you have to clean your data, you have to run it through the algorithm to train a model. That is kind of different. That equation, that balance has changed, right? And I think it makes for like a pretty unique
yeah, it's very interesting actually, because as you say, like getting those base models trained at this point, I think we just heard a great talk from Bindu and Noah, and they discussed also how like it's a very capital intensive business these days, right? To get those foundation models out, we're talking tens of millions of dollars to train some of those. So the fact that there's now opportunities are out there for us to take the work that is done by, and the amount of capital that's been invested into those, and then modify them and customize them to do the specific stuff that we want at fractions of the cost, like really fractions, thanks to the many interesting methods that we're going to discuss today. That's a huge opportunity. And that's an opportunity that, as you say, hasn't been around really. There's no exact parallel for this perhaps in history. I don't want to be hyperbolic, but yeah, it's really quite unique. Yeah, like and the way that I mean, the human capital aspect is also quite interesting, because there's a lot of technical expertise, as you pointed out, that goes into really making these models work. Like they're not always that easy to get to work. So even on the customization front, it can be quite tricky to sometimes to figure out exactly what it is that how it is that you get your models to do what you want to do. But we'll touch on some of that today. So yeah, I mean, coming back to the question, why would you want to customize our LLMs and not just use Llama directly or GPT-X directly?
Yeah. So so the very simplest form of customization that anybody does when they go on to ChatGPT's website or whatever is to ask it a question, right? So it's going to respond to your question. So you've given it some input and it's going to come back with some input. And I think it starts from there. So you know, we want the model to respond in a particular way. We want the model to specialize in a particular task. And these base models are trained on you know, on a vast collection of like human knowledge that is accumulated on the web and is available in digital form. That balance, that, you know, there's a particular balance of information in that corpus, and that might not always line up with the task we're trying to do. A lot of textbooks, a lot of fiction, a lot of poetry. Maybe that's why ChatGPT is so good at poetry. Lots of code. It like that's clearly trained on a lot of code. But you know, we might want it to do a slightly different task. We might want to make it focus on recipes. It already knows about recipes. It does pretty good on recipes up front. But maybe if we force it to like learn a little bit more, be a little bit more focused on recipes, will stay on topic. It will do special things with recipes. That's the general idea. So we're trying to shift the model's behavior to a domain that is of more interest to us because it somehow aligns with our business.
In essence, you're saying that like a generalist model probably can't do as well at a specific task as something that you customize to some degree, right?
Yeah, and to some extent, it is a bit like, you know, the parallel to humans. I mean, like many people are capable of many things. It depends on like what they want to do, you know, what they want to do with this thing. What you want them to do, you let them train, practice, and they get better at doing that fun stuff.
Yeah, at least until we have AGI, I think that's still going to be the case. That I agree. Like, it's still going to be the case that we will have models that will perform better than the big base models if you train them to do certain things, if you fine tune or customize them to do certain things. So, like, yeah, I mean, you mentioned like coming now maybe a little bit to what are the approaches that you could use to customize models. You mentioned like the first one, which is when people go onto these platforms or whatever, and they type in the question, right? So
so let's get a little bit more into it, right? So like, you know, prompt engineering is clearly emerging as a field. So you know, there is sort of like programming the LLM via finding the right formula of prompting and arrangement of the prompt and arrangement of side data that needs to go along with your prompt to make it do the task you want it to do, right? Like, should you pose, you know, the information before you pass the prompt? Should you pass the prompt? Should you ask it to be verbose? Should you ask it to be concise? All of those details can be adjusted. And so sort of like the simplest sort of first customization you can do with an LLM is kind of a template for a prompt generation, and then you run the prompt. You get some input, new input, you run it through your template, you produce a prompt, you run it through the LLM. Now it goes from there, it gets like succeeding, like you can get very complex with this.
I'll just throw in one thing. Just throwing in one thing on engineering. I think like it's actually not always very obvious that what is the best prompt even. Like that's, even though I guess prompt engineering is a little bit memey in some sense, I think there's a real element of engineering to it where you really have to learn how these models operate on different prompts. Like, you have to come in with a bit of experience, you have to try out different things and see how they respond. It's not the way to extract the information from the models is not always necessarily obvious a priori. And a lot of the times there's a lot of papers out there which show that these models have information, more information than we think. And it's just a matter of extracting it with the right set of prompts, maybe.
Yeah. I mean, there's only one line for people interested, like one whole like sequence of work is this chain of thought reasoning, right? Where you try to make the LLM not do the task all at one shot, but you ask it to kind of like sequentially do the task by cleverly prompt engineering step by step and forcing it to go through the steps. There's also like plenty of interesting work on fine tuning when you have supervised data that like comes in that form. But even without like any fine, like, you know, gradient descent, just doing this sort of like sequential, like turning tasks into sequential prompts is a powerful form of engineering, or is a powerful tool developing around these elements. Yeah, actually, on that line, and I mean, like generation, actually, we were just talking about like, you know, having it generate small steps. I think we should also underestimate like the amount that can be configured and how these LLMs generate text, right? So you have some models generating probabilities, but you don't have to pick just the most probable next token. There are a number of choices that are made. And, you know, beam search was the original one but now you have this differential like contrastive search where you're trying not to generate text that has been generated previously, or you are trying to generate text that's generated previously, right? So for example, if you're asking the model to recall something from a passage of text, you might want to bias towards stuff that has appeared before, even if it's not the most probable next token according to the model. So the various tricks you can play at generation. There's the fact that like you can randomly sample generation hundreds of times and do interesting things with the repeated examples. You're trying to generate training data. You're trying to generate questions for exams. Well, you don't need to pick one question. You can pick 5 phrasings of the question and have them all be different. Right. So there are tricks even on the generation side. Should we keep going deeper? Like there's like we have the whole.
I mean, one thing I'll throw in there is like, yeah, all of these parameters that are controlled by things that people will have seen, like the temperature parameter on these platforms, temperature, like the frequency penalty, things like that, all really come into play. And it's also interesting that you mentioned like that you can have multiple different samples, and I've seen even in like there's like applications of the fact that you can sample so many different varieties from these LLMs, like the AlphaCoder paper from DeepMind. I remember one of the main things they do is they just produce loads and loads of different samples just so that they can use that against the test cases, because what they're trying to do is trying to build a code generation model. And so they have some tests to determine if the code passes or not. And one of the tricks they use is just to generate lots and lots of samples and say, this is and whichever samples pass the constructed test they've made are the ones that they're going to choose from for deciding in the final submission. So yeah, definitely, I think that's an interesting one. Yeah, there's all these. So even in the prompt engineering level at a generation level, before you even begin to unwrap the layers of the hood of the LLM itself, there's all the dials on the top. But then once you start playing with like what you can actually do under the hood, I think you really start to explore the possibilities, right?
Yeah. So, I think if you can't talk about deep learning without talking about gradient descent. So let's talk about our first gradient descent based approach to like fine tuning here, right? Generate. So we can generate training examples like that. We can mask it out so that the model only focuses on what it needs to generate. So now what can we actually fit? Well, we can fit the prompt. We have the embedding weights of the prompt. We don't know what actual language we want to use, but we can let the model learn what are the best embedding weights to generate those supervised examples. So we freeze all of the weights of the model, which is the vast amount of the weights, because the weights are like, billions of parameters. And we have just these like, few thousand floating point numbers that we need to fit, and then we start doing gradient descent on those, and we start minimizing the loss on our supervised set, and we find the ideal prompt. And the ideal prompt, maybe it corresponds to English, probably not. It probably corresponds to some strange space of like what the model receives as an input, but it's a powerful idea, and I think there are many derivatives that come from this. Like, can you use this? Can you then tweak that prompt? Can you get a base prompt and generate more prompts from that with minimal additional training? Those kind of questions naturally arise from this. But this is one immediate sort of like the first step to like having some small amount of trainable data that you can actually fit to your supervised problems.
Yeah, so like just to reiterate for everybody who's watching, the idea there is simply like you have the supervised data, and now instead of using it to backprop and update the weights of your model, you're updating directly the prompt itself but not the tokens, like the language itself, but in some kind of embedding space, right? That's what you're doing.
Yep, you're updating the embeddings for those tokens. So they may not correspond to any real world token. Like nothing in your token dictionary would actually correspond to those weights. It's some unique superposition or combination of those weights that the model is learning. So by the way, one thing we should clarify, like why do we want to do this as opposed to just updating the model weights? Actually, there's a very good reason. Like naive updating of these highly trained models will just break them, right? Like so our first goal is not to mess up this nice model that these people have, like, so generously trained on a large amount of data and have it learn about the world and so on. And it's, there are a lot of weights. It's very easy to overfit. We're training with very small data sets. We can easily overfit or train the model to just memorize, right? These models are perfectly capable of memorizing your answers.
I think that's a very important point here. Actually, we didn't really touch on that, but if you just took the naive approach of training specifically on your data set and leaving everything else as a standard, like machine learning pipeline where you just update all your weights, the model will lose all the benefits of the fact that it's been trained for millions of dollars and a very long time. All of that information will probably start to dissipate quite soon, right? So that's why you want to take an approach like this. And this soft prompt tuning approach is a little bit like the best possible prompt engineering you can do, right? Because you're letting the model, the gradients essentially tell you what is the best possible prompt for the task you want to achieve.
Yes, for the supervised task. So, I mean, I think you trade the ability to manipulate the prompt with the optimality for this specific task, right? So when I give English language prompts, it's fairly easy for other humans to manipulate it into a new task. And so that's why I think we have to relearn some of these we have to rebuild some of these capabilities of being able to manipulate the prompt once we've trained it, because English language prompts have the advantage that they're easy to manipulate and adjust for new tasks, whereas soft prompt tuning is more about like specializing to a particular task. So it has trade-offs, like everything, it has trade-offs, but it is unique in that, like, it is an ideal way to get to the optimal prompt in a principled way, right? Otherwise, what are we doing? How many prompts are we going to really test? We're going to test 500. We're always going to, we're going to be subject to our own biases about how that task should be framed or whatever, right? So the prompt engineering without this guidance is a little bit like open-ended.
That's definitely true. Yeah, I think like with and also with the soft prompt tuning, one of the disadvantages, as you said, is that you need a different set of soft prompts for every single task that you have, right? And that's where it also gets a bit tricky. Maybe if you have a wide range of tasks, it's you need to train a bunch of different soft prompts. It's not quite universally applicable. Although, as we know, there's some research being done on that, on maybe generalizing that idea as well.
Okay, so I'm like vaguely following the chat too, but like I'm seeing like a couple of people asking about an example of a soft prompt, like when you would maybe want, I mean, if I'm understanding the question correctly, when you would want to do soft prompt training. An example would be like, let's say I want my model to answer in a particular JSON format, right? So I want my model to always answer with a particular JSON structure, which is follow some schema. I can come up with various ways of phrasing that in the prompt. Like I can give it an example of the JSON. I can describe it as some kind of like, fancy JSON description language, like, I don't know, XML description, like they have XML. Like the very ways you can prompt it, but we don't know what the model likes best. We don't know how the model best consumes an instruction to produce JSON according to a particular schema. So since we don't know that, we can instead train a soft prompt. So we basically train a portion of our prompt space. We're going to give it some input that we want it to encode as a JSON, but we're going to keep a portion of our input to like really make the model want to answer in that schema. And we can easily fine tune it because I can generate unbounded number of JSON examples conforming to the schema that I want the model to like sort of like comply with when it is generating data. And so if I have a lot of those examples, I tune the model's prompt to say that, you're going to produce data always in this JSON schema for use by some downstream system. And I won't try and guess what prompt best achieves that. I'm just going to like train you into submission so that you, answer with the prompt, the schema. So that's maybe an example.
Yeah, I think that's a great example. I also see this other question where they're asking, so are you saying that you should never add domain-specific data to these models? That's definitely not what we're saying. You can add domain-specific data, but you have to be very careful in how you do it. Because if you train specifically on domain-specific data, nothing else, and you let everything just proceed as a normal training loop, you will probably end up damaging the core model. That's what we're saying. So.
So yes. So I think Arka, why don't you actually why don't you fill in details on one technique that we've seen that's pretty successful at preserving the model, but also safely adding in domain-specific data?
Yeah, sure. I think this is the most popular approach there is right now. It's an approach called LoRA, right? Low rank adaptation weights. This is a paper that I think came out probably around last year or so. And the idea is that instead of updating all the weights of your model, if you have a domain-specific set of data, like the person in chat says some electronic health record data, and you want to imbue that information in some way into your model, then what you do is you apply these LoRA weights. Now, LoRA is taking the base weights of your model and projecting them into some lower rank dimensionality. And so when you do that, you massively reduce the number of parameters that you have to train on. And actually what it's doing is it takes the base weights and it adds the low rank projection onto it. So it's sort of like, you can imagine, like it's a small modification. It's a very low dimensional low rank modification to your original base weights. So the effect on the number of trainable parameters will be quite small. And that's really good, because a lot of the times, if you were trying to train the entire model, that's billions of parameters, what fit in memory and so on. But with LoRA, you can get orders of magnitudes. You can get 1,000 times less parameter, less memory usage, because you have 1,000 times fewer parameters to update. And it's actually still turns out to be very effective in terms of this fine balance between preserving the behavior of the base model and the general world knowledge, the general understanding of language, the general understanding of code, all the things that we really care about in LLMs, these large LLMs. But still, with those LoRA weights, fine-tuning to your data points. Yeah, this LoRA approach has turned out to be a very popular approach in research in the open source community at the moment, and it's something that we use as well. It's really, you can do a LoRA fit of your model within, if you have the right hardware, if you just have a few GPUs, you can probably do that depending on the size of your model and the size of your corpus within a day or 2 days, and at the cost of maybe in the low hundreds of dollars rather than in the millions of dollars. So it's really quite a game changer there.
I mean, one interesting thing that we've done with this is actually it makes it very convenient for serving, because you can take one base model and you have these low dimensional, low rank weights, which are tiny, right? Like 1,000th the size of the original model, and you can keep them all loaded on the GPU, and you can very quickly flip between models. So if you have one model that is specialized in widgets and another model that's specialized in clothes, it kind of like, it's very cheap to serve both, because you can the model can flip at serving time. You can flip between,
right, because it's just adding on. It's sort of like just adding on a different set of weights that you have, and those new weights are very quick to load in and out, right?
They're tiny, and actually, I mean, you can load them in and out cheaply. They're small enough that you can fit like a dozen on the GPU along with the main model and not notice, right? It's like we're talking about 0.1%. So usually you have 0.1% of space left on your GPU. Yeah, if you have a couple of percent left on the GPU, you can stick them in.
Yeah. But then why? I guess the natural follow-up to that is, instead of doing LoRA, why would you not just train certain layers of your neural net instead, right? Like the classic approach would be something like freezing the bottom layers and then only training the top layer of your big LLM stack.
Yeah, I mean, I think there's a couple of reasons. One is, it's very hard to reason about LLMs. So my first, we've tried this, and you start with the top of the stack. You believe that's where you should work, but who knows? Like maybe you should train every alternate layer. Maybe you should train every fourth layer. Only the bottom of the stack, whatever. Embedding layer. Should you touch the embedding layer or not? Who knows? So that's one question. It's kind of like it feels a little like unprincipled. Whereas like LoRA, you kind of like just touch every layer and you're done with it. The second is actually it's hard to train a small portion of the model when selecting by layer size. So if I select like the top layer, that's like 5% of the model. That's 5% of the weights on a multi-billion parameter model. That's a few 100 million weights, right? So I think that it's not as easy a way to get to like training a small amount of the model. You have to do some very silly things like training slices of the matrix or something like that at each layer.
Right. Yeah, exactly. Because even if you just took the top layer, you're already looking at like it's only like 2% or 3%. You still have 2 or 3% of the parameters remaining, which is still 10 times or 20 times more than LoRA, and you're not even making sure you're adjusting things in all the different.
Yeah, you're right.
Yeah. That makes sense. That.
So the other reason is this. There's nice properties of separability and so on that come out with LoRA. Like you can like pop off the model and plug and play. You can adapt it twice and have like the 2 different layers. Maybe first domain knowledge and then instruct training. So it's definitely a more principled way to work with like lower rank training. It acts as both regularization and achieves the thing of having much cheaper training for the model.
Yeah, and actually, if you look at like what people have been doing in the open source community, I think LoRA is the method that has taken these open source models as close to the closed source models that exist right now as they're the ones that are sort of doing the best in these various benchmarks. Now, benchmarks are not always to be trusted fully, but because they have their own biases and so on. But basically, the best models that are out there in these in the open source, at least, seem to be coming out of this LoRA approach. Like Alpaca, Vicuna, those are the ones that are very well known, and they're all trained with just a small amount of data, actually, quite a small amount of data, and this LoRA approach. And just by doing that, you get a lot of performance, like really significantly closing the gap on the closed source models that are out there.
There are a couple of questions coming in, so I'll quickly answer that. I would say I don't have much experience with training like in individual separate LoRA things and then adding them back together. My first guess is that would not work very well, but more the point that you can stack them. So you can apply one LoRa layer and then continue training for some other task on top of that. So usually it won't be another task, but you're training for domain and then you're training for like style of answer, right? So let's say you're training to learn about like the health domain, and then you're training to answer in a Q&A style. And those two can be 2 separate LoRa layers. So you can play with the second layer independent of the first. So you first build in health into your model, and then you build in some quality of like how it answers and so on. And those can be kept as separate modules that get added in or not. Whether they can be added in separately, that actually goes to there's a whole separate set of papers about that. But maybe we'll like leave that for another time.
Yeah, actually, it's very interesting because I think that's not a settled question at the moment. And at least from what we've seen a little bit internally, it does look like you can just like the different LoRa weights sort of capture different modes of operation, and you can almost just add them together. It's almost like style content, and it does work. But this is just playing around with the models day to day and seeing how they operate. I think there's a lot more to write about that, really. So the LoRa approach is definitely one which is sort of like, and now you're not operating in prompt space anymore, right? You're operating in weight space. You're really changing the model directly. So it's a lot more powerful than prompt engineering or even soft prompt fine tuning. And you can do a lot with this. What should we touch on a little bit on how this compares to something like learning via reinforcement learning from human feedback?
Yeah, I think so. I mean, like, I think even before, like maybe or actually as a step to like reinforcement learning with human feedback is the other thing is, I mean, these LLMs are at the end of the day, just like people were doing with BERT, you can stick some arbitrary head on them and have them do any other task, right? So that's That's the first idea. So we can use these LLMs to train reward models, right? So that's the key. I think that's one of the key ideas here, that the model has learned a lot about the world. Now we can make it do a task, let's have it rank answers, right? Like let's have it rank a good answer from a bad answer. Okay, let's have it rank an unsafe answer from a safe answer, and so on. But we need something to rank. So now this is where supervised data comes in. This is another place where like a lot of people have done a lot of good heavy lifting in the open source community, private companies that decide to share their work, but they've generated human labeled data sets that have gold standard answers. We can train the LLMs to like recognize these answers as good answers or bad answers. And now we have a reward model that can like rank answers as good or bad. And then what we do with that depends a lot on like what our business use cases. And I think honestly, for like 90% of businesses, the reward model is the end state. Like I can use it to rank posts, catch bad posts, whatever like people were doing with BERT, but now I can do with the full power of an LLM behind this, as opposed to something the size of BERT, right? It's substantial scale difference there. But more advanced use cases are that you put this back into a training loop, and then you follow the RL training approach that has been published by OpenAI and so on, where the reward model is used to update the base LLMs generation to generate better answers, or answers that better line up with human feedback. So in that context, we were talking about this, but like in that context, it feels like the reward model is a way of like scaling up human feedback, right? Like you have X number of labels that you can generate, but then you can generate it too much.
But I think there's
I think like, yeah, so the question, the questions in the thread also, like, is RLHF something that like mere mortals can do? And I think honestly, unfortunately, the answer is no.
I agree with that.
It is hard. It is hard to like build these loops. It's hard to like generate data at the scale that this is meaningful over what already works. So I wouldn't. Maybe I'm too conservative, but I wouldn't bet my business on being able to train an RLHF model, or bet my sort of like.
I think I'm on the same page. Yeah, you would need a lot of data to begin with, and RL training also is way more difficult in general than doing.
It's just fiddly, right? Like I think for people who work in the space, it's just very fiddly. It's hard to get converged.
Extremely fiddly. There's a lot, like I remember, like in my past experience with RL, you can change like this is true also nowadays, I guess, to some degree for supervised learning, but you can change the activations from like ReLU to something else, and it'll completely change the trajectory of the models. They may just not converge at all. Convergence is very hard to guarantee in RL setting as well. Like it's not always the case that you're going to get the same training curves. Any RL paper, they're often RL papers, the curves that you see, the learning curves, are run with 10 different seeds because there's that much variability in them. Like you really need 10 seeds or 20 seeds to see the true performance of an algorithm, versus in supervised learning where, yes, there will be some variance from run to run, but it's usually significantly less than just the amount of instability that we have in RL. So it's a lot more difficult to apply. And it's also the case that I think that you'll need significant amount of CPU power, because you'll be doing distributed training, you'll be doing, you probably don't need as many GPUs, but you definitely need.
Yeah.
Well, actually, in this case, you would need GPUs.
In this case, you need, because both models are GPU based. So even the PPO model is actually a GPU based. Yeah. Okay. One thing we should quickly like touch on, because we kind of because it's quite easy to go down this like RL like sort of like black hole or whatever. But I think there's also like a lot of interesting work building on the same idea of like adding a head to LLMs, is adding a small piece of architecture to the LLMs, which is the part that you train, and then you leave the rest of the architecture constant. And so there's some interesting ideas here for like multi-modality, or bringing in some other data, right? So like, let's say you want to do some LLM thing, but your input is actually numbers. And you don't necessarily want to go through English language as a way of feeding these numbers into the model. So you can have a small piece of architecture that turns these numbers into an embedding, just like you do with soft prompt. and then train a combined model to achieve your goal. Like I'm being a little coy here by saying numbers, but those numbers could be an image, right? So what is an image other than a set of pixels that are, have some intensity or whatever, right? So there's been some work here about like extending LLMs to work with images and so on, with just fine tuning. So not baseline training, like I don't know what OpenAI exactly is doing for their multimodality, but there have been some interesting results on being able to add some degree of multimodality even with just a pre-existing trained LLM by.
So the way these approaches work is generally they take the image, let's say, and then they have a separate bit of architecture that's like a vision module over that image, creates some kind of encoding of that, and that encoding is used to condition the base LLM. Is that the general idea of these models?
Yeah. I mean, it's added in as an additional attention thing, not necessarily condition, but actually, like it generates entries in the attention context. So some amount of the context is expanded with a portion there. You position and code them differently, these positions, so it's clear that it's not part of like the text encoding, and then you let the model just like pay attention, attend to it, just like it attends to everything else.
Yeah, I think that's a very interesting area.
Yeah, and you can avoid cross attention. Like you can avoid like that model getting confused by masking off the attention between each visual element. So only language to visual element attention is allowed, not the other direction, so that you don't mess up the models.
Shall we chat a little bit about what some of the challenges are with going down this customization of LLMs route?
Yeah, so in my mind, the single biggest issue that we keep running into, I think everyone runs into, is like, so this idea of like customizing LLMs to a domain, I think can be a bit of a boondoggle or whatever, like is a very challenging issue, because LLMs know a lot, and it is non-trivial to figure out whether your LLM is hallucinating or remembering, and so you train, you basically train on all of your domain knowledge, and then you ask it a question and answer something that looks plausible. But how do you check it? Well, you search your domain knowledge. But now you're back to basically like searching your text again to see whether it remembered something or it hallucinated something. And it is not, and the insidious thing is, I think like hallucinations become much easier if your domain is common, right? So if I am training about some completely new domain, like I'm training my model on something that doesn't even look like English, the model probably won't be very good at it, but like you kind of guarantee that it won't hallucinate this because it's not remembered it from like its previous training. But that's not most of the time what people are asking for, right? Like you're asking it to like learn some custom domain about like real estate documents, but it's read a lot of real estate documents. So when it comes up with an answer for you, you don't know whether this is a real estate document you trained it on or one that's like learned before. So I think fine tuning is much more like successful at like doing a particular task or changing the style of the answer, like you want it to answer in a particular way, or you're going to open book type questions where you give it some information, you ask it to summarize, so you know that it's paying attention very specifically to the summary context, as opposed to like pulling it out from somewhere in its weights. So some of these things, I think, and also like this, the summarization thing, there are ways to fine tune. I think Arka's looking to this, like ways to fine tune it to ensure that it stays on track, like it doesn't like deviate from the summary input or whatever its input context too far. So you can train the model to do that. But a general thing like hallucination is definitely a problem. I don't know, Arka, do you have others that you think are interesting challenges?
I mean, I'll just throw in on the hallucination stuff. I mean, definitely it's, I think, one of the biggest challenges of LLMs right now, and it's not a solved problem by any means. Like it plagues every LLM, and I think all people who use LLMs, GPT, whatever, frequently will tell you that the biggest issue they have is that it hallucinates. And yeah, there is no great solution to this yet. Now, I have seen a couple of papers, which I thought were pretty interesting, going in the direction of like figuring out ways to reduce the incidence of hallucination to some degree, and these ideas can be something like having a very small set of supervised data and then training a very small model, essentially, on top of your LLMs to try and direct the activations in a direction that is more truthful and less hallucinatory. Now, there's a couple of papers on this idea, and it seems to work reasonably well in these papers. Like there does seem to be like a very simple direction. Like there seems to be a direction you can move your activations in this very complex, high-dimensional activation space that can achieve this to at least some degree. It's not perfect by any means. So yeah, we'll see what happens out of this, but that's like the kind of research that's being done in this field at the moment. But I think, as I said at the top, there's no perfect solution to this, and I think one of the other big challenges that is getting a lot of discussion at the moment is also the limitation of the context length of LLMs, that you can only feed them a certain maximum amount of data in the prompt window, and that's all that they can really deal with. Now, there's approaches to generate from your database what you need for that specific query, and then fill in the prompt with that. But at the moment, we also have run into these issues of like, we just sometimes wish we had a larger context window. So yeah, maybe you can talk a little bit about solutions to that, Siddartha.
Yeah, I mean,
what's going on in there anyway? Yeah,
I think it's another pretty active area, but I mean, I think there's a general understanding that like the models are not fundamentally limited to that context, because it is attention based in principle. With the right position encoding and the sufficient compute, you can expand it. There are these various tricks like KNN, so that, you know, even if you have 100,000 contexts, you don't attend to every one of those 100,000. You just find the top n positions that are coming up in the softmax and only include that for the next step by doing a KNN search, as opposed to an exhaustive dot product match or whatever, right? So I think there are approaches, but I think one of the key limitations they're finding is the positional embedding itself. Like, there are many choices made when training these maze models that fundamentally do make or do not make the embedding extrapolatable, like basically applicable about outside the range it was trained in. And I think there's going to be, I hope there's that the open source models and the public models go in the direction of like, you know, adopting extrapolatable embeddings, as opposed to ones that are very tied to the training windows and the training context.
Yeah, absolutely. I think we're running down on time, right? So maybe we should here just try and close off a little bit. If you had a message to say to all the people who are watching in terms of how they can make their custom model unique and different, and why they should be doing customization, what would you say to that?
Yeah, so we had just a minute left. So I think we unfortunately didn't touch on the most important thing. The single most thing you can do is bring interesting data, right? So like, these LLMs are trained on lots of good, high quality data. The only way you're going to get them to do better on your task is if you bring new data that gets them to learn about your task. So at the end of the day, you know, the single biggest unique thing that we can bring to an LLM, I think, is high quality data. And I think people were mentioning even evaluation and all those things. All of that depends on like the kind of data that you have that will allow you to evaluate the answers, to train your answers, fine tune the answers. So really, you know, rather than investing in like fancy GPUs or training time, I think you're much better off coming up with, you know, 5,000 high quality examples and a little bit of training time, versus 100,000 poorly generated synthetic examples that you hope for the best by playing games with the architecture or LoRA or whatever else. You know, there are a whole bag of tricks, and we keep coming up with new ones of those tricks, but we will not be able to replace good high quality data for model quality.
Yeah, I think it's worth it. Yeah, exactly. What we've seen so far is that even having a small set of data, you really don't need that much to be able to get great results in whatever task that you're trying to do. These models have a lot of base knowledge, and they just need that little bit of a kick from your high quality data to really get good performance, sometimes amazing performance on whatever tasks that you have. And then you'll have a unique proposition, right? You have this unique LLM that's custom to you and that's able to do these tasks that maybe nobody else can, because you have the data and nobody else has the same data that you do.
Yep.
Indeed. Okay, I guess we're just about up to time. Yeah, thank you guys very much.
Thank you all.
I don't know